Linear independence. A set of vectors, say v1, v2 to v sub n, is a linearly independent set if the system ax equals 0 has only the trivial solution where A is the matrix where its columns are the vectors v1, v2 through v sub n. So basically, if your system is or can be represented as the columns of a matrix that are these vectors, and you augment that with the 0 vector, and you get a leading 1 in every column, and you don't have any free variables, then only the trivial solution is the solution to ax equals 0, then you've got a linearly independent set. If you get free variables, then 0 is not the only solution. The trivial solution is not the only solution. And we say that those are dependent. So here's an example. Are the columns of A linearly independent? Well, we'll need to check the system ax equals 0. So we augment this matrix with 0. We're going to row reduce it. I've already got it in my calculator. So I will just row reduce A. And we get this system. That's a 0 there. And I've got a pivot in every column. And if I assign variables here, this says x1 is 0. The second row says x2 is 0. And the third row says x3 is 0. So only the trivial solution is a solution. So we say, yes, the columns of A are linearly independent. Now there are some ways to check dependence without having to do the row reduction. So it's kind of simple, easy ways to check. First, if one vector is a 0 vector. If you got a 0 vector and you row reduce, you're not going to get, you're not going to change that 0 vector, meaning you can't get a leading 1 in that column. That column's going to be a free variable column. So if you got a 0 vector, then they're automatically linearly dependent. If one vector is a multiple of another, or if one vector is the sum of a multiple of one vector and another, then the set of vectors is automatically linearly dependent. So if you can write one vector as a linear combination of the others, then we say that those are dependent. If you can't write any of the vectors as a linear combination of any of the others, then they're independent. If there are more vectors in the set than there are entries in each vector, then they are automatically linearly dependent. If you've got more columns than you have entries, right? When you row reduce, you're automatically going to get a free variable because you don't have enough room to get another leading 1. So let's check these sets of vectors and see if we can tell if they're independent. The first set has 4 vectors, but only 3 entries in each vector. So on number 3, if there are more vectors in the set than there are entries in each vector, then they're automatically linearly dependent. So these are dependent automatically. I already know. I've got too many vectors. When I row reduce, I could get a 1 here, a 1 here, a 1 here, but this column will end up being a free variable. And it could, it could be something different, but I'm automatically going to get a free variable here. This set, again, is linearly dependent because I have this column of zeros. I have a zero vector. When I row reduce, this zero vector will not change. It'll still be all zeros, and I can't get a leading one there. So this will be free. Look at this guy. So when there's two vectors, you want to check to see if one is a multiple of the other. So let's look at this. So how do I go from 2 to 3? So I could multiply -2 by -3 halves, and that will be 3, right? What about here to here? Can I multiply by the same -3 halves? So that would be -6. So it's looking good. So let's try -3 halves times the first vector and see if we get the second vector. All right, so this is 3. This one is -6. 3 halves times 6. With the negative, it's going to be -9. -3 halves times 10. That's -15. And oops, we've got a problem in the last one. So those are not the same. So I thought we could get a -3 halves times the first vector would give us the second vector, and that would make them dependent. But it turns out they tricked us here. This negative sign here means that these aren't the same. So these are actually linearly independent.